Good evening, this is Professor Khan, and this is week 5 of Energy System Technologies, Heat System Design, est-204, and this week we will be talking about insulation. So far we covered the basis of energy. We did cover also heat loss through transmission and heat loss through infiltration, also known as air leakage. And there are some videos and examples about how to do that. Now we will cover some insulation, which means to reduce heat loss from both transmission and infiltration. And so let's get started. Okay, going further. Alright. So learning goals, we'll talk about insulation types. Recognize facing and barriers. What are those? What do they mean? How do they help us reduce heat loss? We'll talk about the options available for retrofitting insulations. If you go to a house and there is not enough insulation, how do you add some insulation, and what are the options available? And again, these options are always available in many forms, and they do evolve over time. They improve and they get cheaper and they get more versatile, so we'll talk about that. And also it's good to be updated about what is available now in the field. So we'll talk about also the best practices of new construction. So new construction probably have better materials. There's a lot of facings and walls that are already pre-insulated. However, we can still retrofit older structures, but it will be a little bit costly. Okay, so talking about the equation that I always talk about, which is this equation. I kind of manipulate it a little bit. It's usually Q equal area times U times delta T. And so this time we're talking about this part only, which is the U factor. We talked about insulation, how does it reduce in transmission by adding to the resistance. So we did a couple of examples when we added the resistance of insulation to the wall, and you see that in week 3. So insulation does add resistance, and it can also improve heat loss by infiltration more than 6 times. Why? Because we said when we change air with the outside, we're bringing in cold air or letting out hot air, which is again costing us a lot of energy. We also would love to have uniform temperature over a surface. Also prevent wintertime condensation. We'll talk about that, especially when it comes to attics. And insulation could also add structural strength. So it might not be very common, but it does do that, especially if we have plywood or or some kind of structures with dry walls. So it does add some structural strength. Also, another benefit of insulation is reduction of noise and vibration. Probably you will know about that if you live in apartment complexes or those condominiums. So insulation does provide us with some barrier for sound and vibration. So again, that's another advantage as we go along. Okay, so is insulation always a good idea? That's a good question. So do we always add insulation to infinity, and is it always going to be good? The quick answer is no. I mean, there's a limit to what insulation can do to reduce the heat loss. And here we have some function between density and R value. If you look, for example, these are example of very common insulators: fiberglass, rock wool, polystyrene, and polyurethanes. They do not change by density because they are foam. But the other ones, as we increase the density, as we pack more, we lower the R value. Can you take a second and think of why that is? It is because we are changing the structure, we are changing the pockets of air inside that insulation. So we rely on those small little pockets of air inside the insulation to have a better R value. And again, we thought about conduction, convection, and radiation. So for insulation, we have conduction through the material itself, and also we have convection through the small cavities and bubbles inside the material. So density is another thing that we have to think about. I will come back to that later in this lecture when we talk about how if we pack too much insulation we will reduce the R value, and also if we do not put enough insulation with the right density we don't get the same R value. Okay, so how does it work? It's how does insulation work? It stops heat from going through the air. Again, we can reduce radiation and convection through cavities. That's another thing. And so we have foam, we have bubble wrap, and we have wool. Those are materials that, if you think about, they use the air trapping ability to insulate. And we said air is a good insulator, but the problem that it moves a lot. So if we have cavities and we have barriers to prevent the air from moving, probably we will have good insulation. So here's some wall types, and these are some of the most common air wall types, and we see the whole wall R value, including the beams. And there's something also called thermal bridging. I'm not going to go too much into it, but you can see that the whole wall R value does increase when we have concrete, and the more beams you have, the less insulation you would have. So thermal bridging, that's what we talked about, is when we have steel studs and we have some drywall, and we probably have a lot of insulation going through the steel, a lot of temperature going through the steel than the insulation itself. So it's a relatively low R value of steel studs can be improved by insulating sheathing as shown here. So we can put sheathing in front of the steel studs to reduce that. But again, you're still going to have a lot of bridges of temperature to go through the steel. Common R values per inch. That's something actually we talked about again before when we were trying to insulate a wall. And fiberglass, again, bear in mind this is per inch. So the more you add, the more R value you will have. So fiberglass was very common in the 80s. It's not common anymore. Cellulose, blown cellulose. This can be made out of many things. It could be made out of old newspapers. So again, it comes in different qualities. Also, we have mineral wool. That still is very common. Vermiculite or perlite. Those are kind of made of rock wool, and they also have good insulating values. And think about the density. Usually foamy materials have good insulation because, again, they have a lot of air inside mixture. The highest so far we have are the boards, the polyisocinurate boards. They're really good in insulating, and they have very good R value. Okay, so water and insulation. That is something also we need to be aware of, especially when we're trying to insulate basements or we're trying to insulate places where it's very close to a humid area. So if the water fills the airspace that we count on to insulate, what happens? First of all, you're going to have better conductivity because water conducts temperature better than air, so that will lower in turn the R value. And water also can cause us to have ice and ice dams if it condenses, and can cause corrosion if we have studs made out of steel or we have nails. It can cause you corrosion. And also water is the primal way to have bacteria. Bacteria feeds on water, so eventually you have bacteria, and you could also have fungi and mold in your walls. So you want to have the proper the proper facing and barriers to stop moisture from coming in. This is a good piece of information that I want you to remember. It's called thermal mass and thermal inertia. I talked about that a little bit in week 1, and it's the property of the material to store heat and how long does it take this material to dispense that heat. It's energy absorption and storage. It varies, has different values, and it increases with R value as well. So let's think of water, for example. Water have very good thermal mass and thermal inertia. It takes a long time to heat water, and it takes a long time also for water to lose heat. If you have a cup of coffee, it will take a while for it to cool off. Meanwhile, air has lower thermal inertia. Think of cement blocks, rocks, they both have high thermal inertia and high thermal storage. So this is something I just want to be aware of, because the material selection has a lot to do with how much you store heat and how long for this material to lose heat. This went a little bit too low. I mean, for a while people were trying to do a lot of passive cooling and heating using thermal mass and thermal inertia, and it's a very common practice when it comes to hotter climates. If you look at primitive houses in South America or Arizona, you'll see they're made out of mud or stones, because that will store heat. It will take a long time for this rock to heat, so during the day it will not be hot, it will take a while for it to heat, and during the night it will dispense the heat slowly back to the house. So it's a good thing to be aware of. Also, there's a lot of places in Europe and also in California where they use big mass of concrete to store heat during the day and dispense it during the night, and sometimes they have pipes and liquid going through it. It's a big area and field of research. So again, insulation. What are insulation made of? Minerals. It has matters that traps air. We talked about that. So if you think of like fur or hair or fabric, what does it do? Part of it, also the material itself, it's insulating, it does not conduct very well, but also part of it is trapping air. So the softer the fur or the hair or the particles, the more it will trap air, and the air that is trapped, it will not move that much, and it's a good insulator. And if you look at animals in the winter, they have thicker fur because it will trap air, and you have this layer between the body and the hair and the air to insulate a little bit. This material can be made of plastics, glass fiber, and cellulose, and all these materials are really bad conductor, which makes them good insulators. So this is another example of wall insulation. We have the bats, which they come as packed fibers or sheet with foil sometimes, and they are non-combustible. Make sure you read the labels and see where is that suitable and where is it located. And some of them they have certain way to be packed, a certain density and certain thickness, so you want to be kind of aware of that. So these are used between studs in here to fill this cavity. Some of them can be cut, then wrapped with plastic, or some of them require you to have some kind of facing in here. So density and weight. So that's a very interesting relationship. We have to think about volume. Why? Because we have to know how much are we going to pack, how much insulation do we need to pack for that little volume. So density and weight relationship, when you go and buy blown-in insulation, you might want to go with weight, and you will have to fluff sometimes insulation, especially the cellulose, to achieve the right density. So weight is density times volume, and volume of course is depth times width times height. So you can measure in inches, but at the end you have to convert that. This is a conversion just between inches and feet. So to get feet cube here, you have to convert to feet cube. So that's the volume, and the reason we need to know the volume, the volume you can measure, because you want to achieve the right density. If you go, as I showed earlier in that slide, if you become more dense, probably you will lose R value, and less dense, you will also lose R value. So again, you multiply that by the density of the insulation that you want to use for the wall. You multiply the volume times the density to get the weight, because you're buying that insulation per weight, per pound. Whether it's blown-in insulation, small particles of foam, or sponges, or packing, you buy it by weight, and you want to know, you weigh the insulation before you blow it into a wall or a cavity. And that is actually very, very good practice for people who are doing retrofitting and weatherization. Probably if you apply for mass save, they will ask you to have somebody come and evaluate your walls and make sure that they are insulated before they approve you to have any rebates. Okay, here's an example. This is the wall. We went there and we took the measurements. and we would like to find this is the cellulose recommended density per cubic feet, so we need to find the volume, then find what is the weight required for that cavity. So how many pounds of insulation do we need for that? Again, you're going to buy a bag and make sure you put it in there and you pack it. Sometimes you put blown in insulation and you have to wait for it to settle a little bit. You don't want to pack it by hand. You wait for it to settle, then you pump in some more. So if you do the math here, you multiply depth, width, and height. Then you divide by that number shown earlier, and you multiply that by the weight, and this is the amount of pounds you need for that cavity. And again, you use blown insulation for attics, you use blown insulation for walls, for cavities, and so on. Other types of insulation besides blown insulation. We have rigid fibrous insulation, which is used to insulate masonry, steel, and wood building components. We also, the problem with that is it's expensive, but it's very durable and it's good for foundations and marine applications and solar collectors. So they are rigid, they give you a good structure, but also they are strong, so they can have some kind of structural integrity when you install them. Blown fiberglass and mineral wool, these were very popular at some point, but they're not popular anymore for many reasons, because those fibers can leak and they can cause health issues. So blown fiberglass and mineral wools are not very common, but they come packed as blankets or bats. So they made out of waste bat. It has lower RF value because it's not packed the right way, and they are sold in bales. So they are good for some applications, but you don't want to put that in the attic or walls. So probably put them in cavities in the garage or underneath the house, and you make sure the whole cavity is completely sealed. They require blowing machine with an agitator. They have issues. Sometimes there are issues with machines, but I'm sure they have improved a lot since the 80s. Overfluffing lead to extra air permeability, and you don't want that. So you need somebody who knows how to do the weight to volume ratio. So fiberglass should be at least 0.7 pound per foot cube in density. This is some information you can find in the book as well. How much density do you need for each of these insulation? And again, settling is expected, so you put in the insulation. You can put it in an attic. In small, there's a video that I'm going to put online that show you how to do blown insulation. Then you go back and you repack it again. More about blown in fiberglass. Density should not be more than 1 pound per cubic feet for ceiling and attics. A lot of information is given by the Department of Energy, so if you go and I think I'll put the website here, that will tell you what is the recommended insulation for attics and basements. No greater than 1.5 pounds per foot for cubic of wall, so 1 pound for ceiling and attics, 1.5 for walls. Again, that has to do with the weight because of the structural support. Same as we did before in terms of the calculation, because you need to pack it and know how much weight you put in there. Blown mineral walls is denser than fiberglass. It is no longer the dominant insulation. Again, we came up with a lot of other ways to insulate our cavities in the house. This is how it's dispensed. Again, you have to, or whoever is doing the weatherization, you have to have some kind of containers, whether it's made out of wood on the ceiling. You fill it up with the insulation, you wait for it to settle, then you put it, then you pack it again, and eventually this whole thing will be covered by plastic or by some kind of barrier, and it's not to be walked on. So as you can see, there's a path here to walk on. Cellulose, it's basically ground up old newspapers and could be made of other materials, but cellulose is the basis of all plant material. Is treated with fire retardant. I don't know if that's the code anymore in some states, because fire retardant has been condemned to be a safety hazard. It's easy to and fast to blow. I mean, you can blow it out inside walls, and it's very, very kind of fluffy, so it has to be blown and packed a little bit. It has better resistance to air convection than fiberglass because again it's very fluffy and dense. I mean, fluffy and dense at the same time. No, it's kind of how can I say that? It's kind of like cotton material, so it's fluffy but also have some density in the same time. R value between 1 and 2. Some problems: it absorbs more water than wool or fiberglass, which makes it an issue if you're going to be in a coastal area or near a river or place with high moisture. Up to 130% of its weight at humid conditions. So you can think of a problem if you put that in the attic and there's rain or leakage and it absorbs a lot of water. Probably the ceiling will cave in at some point. Not good for coastal climates, again for the same reason, because it absorbs a lot of humidity. Water can damage the fire retardant out. Fire retardant material is dissolvable in water, so if it washed away, it's going to go in the drainage, and eventually it causes a lot of environmental impact. So I think it has been banned in California. I don't know about other states, but this is some of the problem of using fire retardant in a lot of materials. Attic insulation, density of 1.2 to 1.6 per cubic foot, 15% settling, and for wall it could be a little bit heavier, again for the same reason, because of density. Vermiculite and perlite, these are heated rock pellets. They actually pop like popcorns and they have really good density, and they have less voids than other fillings, and they can be packed, and you can use them also along with cement because they're strong. So you can use them with cement and aggregates. R value of 2.4 or less. That's these insulating material. Plastic foam panels. These were common for many applications for the longest time. They keep improving on those. Some of these surfaces are covered with Teflon, so it's non-stick. And those material can be cut or pre-cut to be installed in places. That makes them very, very convenient. They have wood or aluminum sheathing and sometimes some barrier as well for moisture. They also used for ductwork, but I haven't seen a lot of those here in New England because they're very good for cooling but not for heating, because over time if we have fuel oil or gas for heating, probably the temperature will be very high and eventually that will deteriorate this material. They have high rigidity, but they are also susceptible to UV. This is what they look like. They can pre-cut actually, and they have a machine that will cut and do all these grooves, so you can just put them together with duct tape. Another picture of those in place. They look very nice, and they have low weight, so it's really easy to hang and actually modify as well. Pros and cons: they're very excellent in tight spaces, very high R value. They can be used as filling for panels or between walls. They can be sandwiched with plastic, steel, or aluminum. Some of the problems or caveats are R value deteriorate with time. Again, you have to check with the material. I'm sure there's a lot of improvement has been happening to these panels because they're very convenient. Again, they're very susceptible to UV light, but after a while they become crispy and they start to fall apart and become kind of dusty. They're brittle. They cannot stand a lot of weight because they're foam, and so they are susceptible to mechanical damage as well. They're also combustible, but again, it also depends on the material and how they are being treated. I mean, before they been installed. Foam insulation, they can be done by spray or injection. And as you can see, the guy is wearing a space suit here because this material is very sticky. If you ever worked with those foam little cans, it's very annoying. It's really hard to control. So as you can see here, the guy is filling up those cavities with foam, and you have to cut it and shave it to make it even because you cannot control how the foam will expand. They are very rigid. They insulate a lot of noise. They're a good option, but again, it's really messy to work with. I haven't seen that much of foam insulation being blown this way, but I've seen like the cans for some cavities and bats to be installed in place, but it is an option. Foam, again, it comes in a can. It had to be sprayed with an agent. It has great adhesion. It sticks very well, sometimes a little bit too well, and good structural strength overall because again, it fills the cavity and it's very rigid. It has a very good air sealing capacity. The thermal resistance, R value between 6 and 7, and that's per inch foam can have the R value of 3.6 per inch. So if you have 2 inches of that, probably can be 6 to 7. Facing and barriers, those are very important, especially if you're trying to insulate the moisture coming from the outside, especially in basements or attics. So weather resistant barrier, they have some plastics and paper with wax on them. They protect against vapor, and they called fire barriers because they eliminate the air and they are treated with fire retardant material. Facings, those what you actually wrap your insulation with: craft barrier, craft paper, aluminum foil, white vinyl sheathing. And if you can see here, this is where you want to put your layers of barriers between the rock wall to protect your insulation and also protect the air transmission from inside to outside. So this shows you how does the barrier act. So this is the outside here. It is freezing, and inside we have this barrier over here. So the water will go into the wood panel and drips, and this is where the moisture goes in, and it's going to fill your insulation and fill your wood panel, and eventually it'll cause you to have some problems. So water does go through the wood panel. So probably you want to have barriers in both sides. This is how blown insulation is done through the wall. We will dig holes into the wall and put either foam insulation or some cellulose blown in. So you fill it from the top until it comes out. If you're filling like blown insulation, probably gonna fill from the top. But if you fill foam, you're probably gonna blow it from the bottom until it comes out from the top. And I've seen them actually when they blow it from one side in the wall until it comes out from the other side. This is another idea to insulate between floors. So you can use twine to stick bats in the top. As you can see, it's really hard to put foam in here. It will fall back. This is a practical way to put these kind of fillings inside the cavity for a floor or ceiling. However, you want to keep them in place and you want to keep them intact from things to get into it. Again, mice and moth and a lot of insects like to live in that foam because it's warm. It has a lot of cavity. So make sure when you do this kind of barriers that you have the proper insulation to close all these openings so you don't have a lot of vermin living in there. This is the DOE recommendation, the Department of Energy, and I put a link here so you can look it up, what they need you to have for insulation. And zones are pertaining the region of the country. So check that out. It's very interesting. If you notice, like the highest insulation you want to have for the attics and basement, and that's because it's the colder areas, because most of the heat will rise and will cause you to lose a lot of heat and eventually pump in more heat inside the house. Where to insulate? Again, this is from the Department of Energy. These are most areas where you have to insulate to make sure you have proper air sealing and low energy transmission through the house. So mostly joints, basements, you want to have barriers in here, and these are some of the areas that are always neglected because we didn't think about it. We think about the top, but this area will lose a lot of heat as well because in the top is not heated and insulated. So whatever you have as your building shell envelope, you want to have insulated. This is the links for some material you can find in the Department of Energy. They are very updated, and they tell you what to use and what not to use and what has been deemed not practical. Okay, so this is what I have for this class, and I will post this video, and I'll post also another video about blown-in insulation. Please watch that and let me know if you have any questions. Thank you.